So let's briefly talk about what a capacitor is. So a capacitor, at least as far as this class is concerned, will be defined as two conductors capable of holding, and I'm going to write in here in parentheses, wow, that's misspelled, storing opposite electric charges. So for most MEMS-based devices, they are going to utilize what's called a parallel plate capacitor. For the most part, this is because we have difficulty fabricating anything other than simple planar structures because we have flat substrates to deal with, right? So for a parallel plate capacitor, let me just draw one real quickly. Might look something like this in a very generic sense, right? So we've got one lead. Here we have a parallel plate. Here is a second plate. And then here is another lead, right? And so we could apply a voltage across this if we wanted to, get into all that kind of good stuff in a little bit, right? So let me just put some labels on here really quickly. So this is our top plate. This guy down here is our bottom plate. And then here in the middle, I'm going to put this pink material. And this pink material is a dielectric material that's typically insulating in nature. So we don't want it to be electrically conducting so that we pass charge across the plates of the device. That dielectric material for most MEMS devices is probably going to be some sort of oxide or it's going to be air. Those are really the only two options that we're going to have most of the time. I guess technically we could also have a vacuum or an absence of air as well. But our materials are fairly limited. Okay. So for a parallel plate capacitor like this, the capacitance of the device C is equal to epsilon A divided by D, where epsilon is the permittivity and this is typically epsilon R, the relative permittivity, multiplied by epsilon naught, the permittivity of free space, where this permittivity of free space, epsilon naught, is given by 8.854 times 10 to the negative 12 farads per meter. That is a constant of the universe. And if you multiply that by the permeability of free space, you get the speed of light squared, because that's how those things were originated. A is our plate area. And I'm just going to put here overlap because it is possible to have one plate larger than the other plate. So we would typically use the smaller plates area in this particular case. And then D is the distance between the plates. And so we can see that effectively there are three different ways that we can vary the value of a capacitance, right? So if we were able to, in some way, shape, or form, manipulate the area of overlap. We could have some variable capacitance in that way. That's what we're going to largely talk about on Friday when we get into capacitive cone drives. If we can, in some way, shape, or form, manipulate the amount of separation between the plates, we can vary the capacitance. And if we can, in some way, shape, or form, manipulate the dielectric material, typically that's done by moving a dielectric either in between the plates or out between the plates so that a ratio of air to a particular dielectric material changes. And we'll talk about that in a little bit. That can also give us some sort of changing capacitance. That's the one that's seen the absolute least. But these are the different ways that we can effectively use capacitors to sense some sort of thing. Joaquin.
Sure. Just a quick question, for your value for E naught, is that 8.95 or 8.5?
8.854. I apologize. Oh, that makes it look even worse for my penmanship. Does that look more like an 8 or does it still look like a 9? Son of a bitch. All right, that looks more like an 8. Okay. So another useful relationship that we might see is that capacitance is typically given as the ratio of charge to voltage. So let's look at a structure. So I'm going to attempt to shittily draw here a bulk micro machined accelerometer. Okay. So we might have something like this. So I've got a big chunk of silicon here from one wafer. And I might etch it in such a way as to give me a profile like this. And then actually, let me draw this bit here in gray. So this might be some sort of photoresist or something like that. And this guy right here is going to form one of my electrodes, which I'm calling electrode B. Okay. Then here in the middle, I'm going to pattern on maybe an SOI wafer, something like this. Okay. So let me just put, this is wafer 1. Then here. Connected. This is where I'm going to have electrode A. I'm going to have an oxide layer. Give myself kind of a proof mass type thing here. Where this whole structure was formed through bulk micromachining for some second wafer. And then lastly, I'm going to have another wafer here on bottom that's effectively just a mirror image of my top wafer. That's going to be terminal C. And let me just define an oxide layer like so. So here is some wafer number 3. These 3 guys are bonded together to form a packaged accelerometer, right? So effectively we have a top plate, kind of a middle plate, and then a bottom plate here. And these 2 guys need to be electrically connected to each other for this kind of scheme to work. But from a circuits perspective, effectively what we have is here's node B. We have some variable capacitance that I'm going to call CW1. Here's node A. This might be where we take our output voltage for this accelerometer, put it into some sort of amplifier. Here's another variable capacitor, which I'm going to call CW2. And then here's node C. Typically speaking, we might apply some excitation voltage here. Could be DC or AC. And typically speaking, we might apply ground down here. So let's talk our way through some things here really quickly, right? So let's say that this is an accelerometer for measuring displacement in what we're going to call the x direction. So I might draw another simple representation here, right? So this guy is our middle plate, and it is attached to some sort of spring suspension so that it is able to move up or down, right? So let's just define the positive x direction as down. So as this middle mass moves up or down, that is going to cause a change in the distance between the top plate and the middle plate. And it's also going to cause an associated change between the distance of the middle plate and the bottom plate, right? So nominally, we might see some distance d between our middle plate and our top plate, and we might have that same distance d. Doesn't necessarily have to be the same, but we should probably pattern it in that way as close as possible because the math will work out a little bit easier, like so. And so let's say that this particular device undergoes some sort of acceleration, causing the proof mass of our accelerometer to move in the positive x direction. So what's going to happen with capacitance CW1? So CW1 is going to get smaller, right? Because the distance between the plates for that capacitor is getting larger. So we could write this as epsilon A over D plus X, right? Because the total distance is increasing by the displacement of our proof mass. Very similarly, this guy down here will be epsilon A over D minus X, right? Because as our proof mass experiences the displacement in the positive X direction, that gap tends to get smaller, which causes that overall capacitance to tend to increase, right? So what might the output voltage of this thing be? Well, let's figure that out really quickly. This is a simple voltage divider circuit, but now we're using capacitance instead of resistance for voltage division. So I'm just going to put a voltage V here out front. That is our excitation voltage. I don't know how much circuits background all of you have that aren't my undergraduate electrical engineering students or weren't previously my undergraduate electrical engineering students. So I might be going through this in more detail than you need, but I'm going to choose to use the Laplacian impedance here for the simplicity of the math, right? So a capacitor has an impedance in the S domain of 1 over SC. So I might put 1 over, let's just put it as SCW1 for right now. Actually, it should be SCW2 because it should be the bottom element in the numerator if we put node C at ground. And then I would have 1 over SCW1 plus 1 over SCW2 over here for now. Where I'm simply applying voltage division for those of you who may not be familiar with this. To make this math work out a little bit easier, I feel like I'm about to sneeze. Okay. I might multiply through by some things to make this math a little better, right? So if I multiplied by SCW2 over SCW2, this guy by SCW1 over SCW1, and this guy by SCW1 over SCW1, I wind up having a common denominator for all of my denominators that will simply cancel, right? So I'll have an S squared CW1, CW2 down here is going to cancel the S squared CW1, CW2 here and here. And so what this winds up leaving me with is just my excitation voltage times a ratio of S CW1 over S times CW1 plus CW2. The S's also cancel each other out so that this relationship is actually independent of frequency. And so we'll have our output voltage is simply our excitation voltage V times the ratio of CW1 over CW1 plus CW2. Effectively, V times the capacitor on top divided by the two capacitances. So if we substitute in our values for EA, for CW1 and CW2, excuse me, V out becomes our applied voltage times epsilon A over D plus X divided by epsilon A over D plus X plus epsilon A over D minus X. And we could do some simple manipulation like we did a moment ago. So multiply this guy by D minus X over D minus X. Multiply this guy by D minus X over D minus X. This guy by D plus X over D plus X. Once again, we have a common denominator, and we also have a common factor of EA everywhere. And this winds up giving us V, our excitation voltage, times D minus X over 2D. So that we can see that our output voltage is a function of our displacement, and it's scaled by some factor that's dependent on the geometry of the system. Just to take this one very small step further, we could write this as V times 1/2 minus X over 2D. So we have a simplistic system here where our output voltage is in some way, shape, or form proportional to the displacement that we undergo caused by some acceleration of our proof mass. All right, so let me scroll down to here. All right, so let's talk about current through a capacitor really quickly, right? So the current flowing through a capacitor, I sub C, as a function of time, by definition will be the derivative of charge as a function of time with respect to time. Well, charge is capacitance times voltage, right? So this will actually wind up giving us the relationship C times the partial of the applied voltage with respect to time plus V times the partial of the capacitance with respect to time. Let me make that partial a little bit better, right? So this is our total derivative relationship. Most of my electrical engineering folks are probably most familiar with the portion on the left, right? I is equal to C dV by dt, where we are making an assumption there that the capacitance is a fixed value. And in all of our circuit analysis classes, we always had fixed value capacitors. But now all of a sudden we don't. So we have to pay attention to the other part of it as well, right? So we might have a term where it is a fixed voltage times the derivative of the capacitance with respect to time, meaning that our output signal is going to be dependent on how quickly the capacitance is able to change, right? So the term on the left is what's going to be called a displacement measurement. And the term on the right is what we are going to call a rate of change measurement. So let's start by looking at a rate of change measurement. So I'm going to call my capacitor current IC. So this will be some DC voltage times the change in capacitance with respect to time. And I'm going to call this a motional current, I motion. Okay. So for a simple parallel plate geometry, our motional current can be expressed as VDC multiplied by change in capacitance with respect to time. Well, we can split that change in capacitance up as VDC times the change in capacitance with respect to displacement multiplied by the change in displacement with respect to time. Everybody okay with that, right? So for our parallel plate capacitor, just as a quick aside, we know that C is epsilon A over, let's say, D minus X, right? So dC by dx is epsilon A times the derivative with respect to time of 1 over d minus x, where the derivative of 1 over d minus x with respect to x is just 1 over d minus x quantity squared. So this is going to come out to be epsilon A over d minus x quantity squared. So I can substitute that in up here. So I'd have VDC times epsilon A over d minus x quantity squared times the derivative of x with respect to time. Well, I can approximate this. Let me put a note here. So if my displacement is much smaller than my nominal gap, then what does that d minus x squared term reduce to? Just d squared, right? Yeah. So that's going to look like VDC times epsilon A over d squared, and then the change in x with respect to time is just my velocity, which I'm going to call x dot. I'm going to put a little box around this guy. So I'm going to attempt to draw another picture, and bear with me on my shitty drawing skills, and my even shittier SolidWorks skills are why I'm relying on drawings. This is another bulk micro machined device. Instead of having an accelerometer this time, we're going to be dealing with a microphone. Okay, so here's my first wafer. And this guy right here represents a very thin, typically on the order of a couple of microns, diaphragm patterned onto a wafer. Here I've got some insulating material, some more insulating material, and then down below here, I'm going to attempt to draw a MEMS structure, something akin to this. And then, so let's see. Wafer one, wafer two, wafer three, like so. So this part right here represents some fixed lower plate with holes, and the holes are important because we need effectively to make sure that air can pass through easily, because this is a sealed device, right? So we don't want to have too much pressure buildup and things like that, okay? So just for what it's worth, silicon, 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 this guy right here, silicon dioxide. So this is a simplistic representation of a MEMS microphone. So let's say that our area of overlap is 1,000 square microns. Our nominal distance between our plates is 1 micron. We have a vibration amplitude of 10 nanometers, excuse me. And we are effectively subjecting our diaphragm to vibrations at 500 hertz. If our DC applied voltage were 5 volts, let's figure out what our motional current would be for this thing. So from a few minutes ago, we know that our motional current should be given by VDC times epsilon A over D squared times our velocity, right? So let's start by figuring out what our velocity is going to be first, okay? So x dot is just a shorthand notation for dx by dt. Well, how can we reconstruct, based on the information that we're given, what our displacement signal is going to look like? So I feel like we have an amplitude and we have a linear frequency. So this shouldn't be that particularly difficult. One of my EE folks tell me what this is. This is circuits 1 level stuff. How do I reconstruct a sinusoid knowing those two pieces of information? Do what? How do I take these two pieces of information and get a time varying function for x of t that I can take the derivative of? Sure, so I can assume a sine or a cosine doesn't particularly matter because they're just 90 degrees out of phase with each other. So let's assume sine, because I know I'm taking the derivative, I won't have to deal with a negative sign, okay? So derivative with respect to time of something, excuse me, sine something. So what's the something to the left of the sine function? 10 nanometers, right? It's just our displacement. Okay, so the peak value of our displacement. And then what's the part that goes inside the argument of the sine function? 2 pi f times time. Sure. So this would look like 100 pi t, and then the units here would be in nanometers. Absolutely fair assessment, right? So if we have a maximum displacement of 10 nanometers and we are exciting this thing at a mechanical frequency of 500 hertz, this is what our plate displacement waveform is going to look like. We take the derivative of this guy, that's just going to be effectively maximum value times omega times cosine of 100 pi t, right? So that's going to come out to be 3.142 times 10 to the minus 5 meters per second. Actually, sorry. 3.142 times 10 to the minus 5 cosine 100 pi t meters per second. Do what? Oh, it should be 1,000. Oh, goodness. Well, I have made a small mistake there. Thank you. And that is technically going to, you know what? Because I did the math wrong, let's say it's 50 hertz instead of 100. Or excuse me, 1,000. That partially explains why that's better. Sorry for the mistake and thank you for catching that. All right, so from here, we can, for the most part, simply plug in numbers, right? So our DC voltage is 5 volts. Epsilon is 8.854 times 10 to the minus 12 farads per meter. Our area is 1,000 microns squared. Our nominal gap is 1 micron quantity squared. For what it's worth, this micron squared here cancels that micron squared there, so those values aren't going to particularly matter. Then we would have 3.142 times 10 to the minus 5 meters per second, and then we're going to tack on a cosine 100 pi t over here at the end, like so. Running out of room, so let me just sneak it in over here. For this 50 hertz vibration, we're actually going to find that our motional current based on these parameters is only 1.391 cosine 100 pi t pico amperes. Yes.
For the epsilon, do we need to include the epsilon for silicon, the 3.9?
So we don't. The reason that's a very good question. Okay. So let's think about it in context. So we have sound vibrations that we are making. So we talk, the pressure wave that we generate hits our diaphragm, which needs to vibrate. If we had diaphragm, silicon dioxide, and then the bottom of our plate, would our top plate be able to move independently? No, which would mean we'd have a really shitty microphone, right? So we need the top plate and the bottom plate to be able to move independently, which means there needs to be an air gap in there, right? Yeah. For other things, though, we may have some dielectric material, but in this particular case, we pretty strictly need an air gap in order to be able to maximize the vibrations. All right, so if our frequency of excitation were to increase, what would happen? Our motional current would get larger, right? Because it is a rate of change based thing, right? So the faster that we are able to vibrate our plate, the higher our output signal, our emotional current in this case should be. Realistically, we would probably need to tune our diaphragm in such a way, so probably through some sort of mechanical trimming, so that the displacements that we were seeing weren't on the order of 10 nanometers, because obviously if our amplitude of our oscillations is also larger, our motional current is going to be larger as well. Right. So anyway. All right, so let's talk about displacement measurements now, briefly. So our capacitor current in this case is going to be C times the derivative of the voltage with respect to time or CV dot if you prefer it that way. I don't, for what it's worth. Where effectively I'm making a note to point that in these cases, our voltage is changing and our capacitance is constant, right? So for a scheme like this, we can use a single capacitor to figure out what's going on, but very often instead we will use ratiometric measurements, okay? Where using ratiometric measurements offer benefits like increased sensitivity. One of the most common displacement measurement tools that we'll see is what's known as a capacitive Wheatstone bridge. Okay. So for a capacitive Wheatstone bridge, we might have something like this. So I'm going to have my excitation voltage here, V, and I'm just going to say explicitly that this is V naught cosine omega t. Okay. So that's the voltage that I'm applying to excite this thing. And now I'm going to attempt to draw a Wheatstone bridge configuration. So we might have something like this, where here's some nominal capacitance C naught. Here's some capacitance CW1, so this is a variable capacitance. Here's another nominal capacitance C naught. And then here is a second variable capacitance. Right. I'm going to say that the voltage on this left-hand branch is going to be V1. The voltage on this right-hand branch is V2. And we're going to ground the bottom. So for CW1 is epsilon A over D minus X, and CW2 is epsilon A over D plus X. What would our output voltage, V out, is equal to V2 minus V1 be? For this particular case. So if we go back to the beginning here, this was an example of a single-ended ratiometric sensing, right? So we effectively just have one simple branch. So our right-hand side of our circuit is effectively just this thing. So I can see pretty easily that V2 should just be what I have written here, right? So V2 would just be my applied voltage V times a factor of 1/2 minus X over 2D, if I remembered correctly from 20 seconds ago when I scrolled up, which is always a possibility. I didn't, so let me double check that again. Yep, that seems legit. Just looking at this damn thing, what would V1 be? Yep. So when I take the difference of those two things, my factors of 1/2 V are going to cancel each other out. And I find that my output no longer has that effectively offset signal. I'm getting rid of it. And so I'm simply left with an output that is V times X over 2D. And Probably supposed to be a negative sign in there as well, but that doesn't particularly matter to me. And I could get rid of that negative sign simply by doing V1 minus V2 if I wanted to anyway, right? Okay. So that's one of the big advantages of using a Wheatstone bridge over single-ended ratiometric sensing, is that we don't have that extra term muddying things up, right? We get rid of this factor of 1/2 of our voltage here, this offset thing that's constant on both sides. It gets thrown away, and our output signal is directly proportional to our displacement. Now, that being said, very often we might have to deal with things like parasitic capacitances, right? So let's look at something just really quickly here. And this will be the last thing that we'll talk about for today. So I've got simple capacitive Wheatstone bridge. Here's C naught. This is going to be CW1, which will be C naught plus some delta C. This guy down here will be CW2, which will be C naught minus some delta C. There's my ground. Here's my voltage V1. Here's my voltage V2. And let's say that C naught is 100 femtofarads. Delta C is 1 femtofarad. And V is 1 cosine omega t volts. And I want to figure out what V out is. And let's just say that I'm only concerned with the magnitude of our output voltage, right? This should be independent of frequency. So for this particular case, V out is still going to be V2 minus V1. So let's figure out what V2 is really quickly. So it should just be V times the top capacitance over the top capacitance plus the bottom capacitance. Well, I've explained why it works that way earlier, right? So that'll be go away thing. CW1 over CW1 plus CW2. Substituting in here, that's going to be V times C naught plus delta C over C naught plus delta C plus C naught minus delta C. Looks like V times C naught plus delta C all over twice C naught, or V times a factor of 1/2 plus delta C over 2 C naught. We all okay with that? Nothing hopefully too wild or crazy there. V1, I hope by inspection, everybody can see that that's literally just going to be 1/2 V. And so V2 minus V1 is just going to look like delta C, V times delta C over 2 C naught. And when I substituted in numbers for this, I can find them. I got this to be 5 millivolts. So that would be the amplitude of our output voltage in this particular case. Okay. Now let's talk about what happens if we had some parasitic capacitance formed with our substrate, right? CP. So the presence of these parasitic capacitants are generally speaking going to cause our output signal to degrade, meaning that we should expect, generally speaking, negative effects from these parasitic capacitants, which in this case would likely manifest in a lower or reduced output voltage. Now we can see that pretty easily, right? So let's see if we say that our parasitic capacitance has a value of 1 picofarad, right? Now, to be clear, this is a pretty damn large parasitic capacitance, in as much as it is 10 times larger than our nominal capacitance C naught, right? So let's see what effects this would have. So with parasitic capacitances, we can pretty much just jump straight to this result right here, right? Nothing about that part is going to change at all for V2, except that we're now going to treat CW2 as this plus this, because those two capacitances are electrically connected in parallel, and capacitances in parallel simply add together, right? So V2 would look like V times CW1 over CW1 plus CW2 plus CP. So that would be V times C naught plus delta C. CW1 plus CW2 is twice C naught. And then so we've got a plus CP term there. V1 is no longer going to be exactly 1/2 of V, because the voltage is no longer going to divide evenly because the capacitances aren't even, right? So we're going to have the capacitor on top, which is C naught, and then we're going to have C naught plus the capacitance on bottom, which is C naught plus CP, or V times C naught over twice C naught plus CP. So that when we take the difference of these two things, we're only going to be left with V times delta C over twice C naught plus CP. Are we all okay with that algebraic manipulation and subtracting things or whatever? So if we plug in our numbers for this thing, we find out that the amplitude of our voltage is actually reduced down to 5/6 of a millivolt. So those parasitic capacitances there greatly impact the output voltage of our system. All right, that's what I have prepared for today. When we come to class on Friday, I'm going to talk about capacitive comb drives and all of that kind of good stuff for a good 45 minutes or so, and then we'll knock off probably 15 to 30 minutes early so that you guys can start enjoying your Christmas break away from me slightly earlier than you normally would have. All right, thank you for your time and your attention. I'll see you guys on Friday. I swear to God, at some point, I'm going to put homeworks up. They won't be due until after the break for sure.
Yeah.
Yeah.
I just make sure I did arrive a little bit late, so just making sure I'm on stuff. And I wanted to actually ask you about the parasitic capacitance.
Sure.
So in this context, what exactly would that represent? Would that represent just different materials?
So
Because I understand the capacitors is fine, but I'm just curious what the parasitic capacitors exactly would imply in this context.
So in this case, it might be, let me just draw something here. So something like this, right? So this thing is conductive, this thing is electrically isolated. They're generally near each other, and anytime we have two conductors near each other, they're going to form a capacitance.
Right, it's not the
So if-
intrinsic capacitor, but it still forms a pseudo capacitor.
Right.
Still causes services. Okay,
Exactly
I
right.
get it.
Yeah, so it's just literally any two conductors that are generally near each other might contribute something to the parasitic capacitance. So like in the context of electronics, typically your largest parasitic capacitance when you're designing ICs is just your substrate to whatever layer you happen to be working on.
Right.
So you're always, because you've got a big conductive substrate, unfortunately, you've got a big bottom plate capacitance.
Well, unless it's like non-dope silicon. That's the-
Yeah. But even then,
Some inherent, yeah, I
Right.
understand what you, thank you.
Yep.
That's what I wanted.